Hello, my name is Taran A, and today I'll be presenting Lab 5, Magnetic Braking with Faraday. The problem that we're trying to solve today is to calculate magnetic fields and forces caused by a magnet falling through a conductive tube. Theoretically, if we know the magnetic dipole moment, the dimensions and resistivity of the conductive tube, we can calculate the forces at play. This is made possible through the magnetic flux equation, Faraday's law, the PHYS2212 law, and Newton's third law. In this experiment, we have a few assumptions. First of all, we assume that the magnet has a constant magnetic field. We assume the only forces acting on the magnet are gravity and the magnetic force of the aluminum foil on the magnet. And third, we assume that there are no other forces causing magnetic fields other than the magnet and the aluminum foil. For our experimental setup, we require a bar magnet, an aluminum foil roll, a meter stick, and a smartphone with the magnetometer app, and a camera. In this experiment, we measure the dimensions of the aluminum foil roll, then we set up the aluminum foil roll so that you can record the magnet falling through the foil roll, and then record at least 5 trials of the magnet falling through and using this video to calculate the time that the magnet spends in the roll. Here are the measurements from the experimental trials. The length of our aluminum foil was 30 centimeters or 0.3 meters. The width of the aluminum foil was 0.0005 meters, which is a little thin but still worked. The inner radius of the foil roll was 0.015 meters. The mass of the magnet was 0.037 kilograms. The magnetic dipole moment was 3.04 Newton meters per Tesla. As you can see, the trials are on the right, and the average time the magnet spent in the tube was 0.356 seconds. Here's the glow script code. You can see that I've put in the geometry of the code and the properties of the magnet. I use the same dipole B formula that I used from Lab 3. The calculated d flux dt analytic was derived from the class materials. I changed the update rate to 300 so that it would be slower, but still fast enough that it would work out. We have the F net as a combination of the magnetic force and the gravitational force, and we have the velocity and position update formulas to update those respectively. Here's a recording of the glow script. As you can see, we have a parabolic velocity versus time graph, which becomes linear after it exits the tube. General observations. In the model, blue indicates current flowing counterclockwise, and red indicates current flowing clockwise, as viewed from above. When the magnet is flipped around, the dynamics of the experiment remain the same, and the same result is produced. The total time in the tube is similar in the real-world experiment as compared to the computational model. However, the computational model could be made more accurate with more accurate measurements of the thickness of the aluminum foil roll. Lastly, the shape of the velocity versus time plot tells us the magnetic force on the bar increases as the bar moves faster, resulting in the parabolic shape and causing it to accelerate slower. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The force of the experiment would change with the resistivity. With the resistivity of the conductor reduced as close as possible to zero, as with the case of a superconductor, the magnet would stay in place in the tube. It would not fall or accelerate in any direction up or down. What if holes or slots were cut into the tube? How would this affect the ring currents in our model? If holes or slots were cut into the tube, in certain places there would not exist rings of current. As there would be holes, the current would be interrupted at these locations, and as a result, the magnetic force would be less, and this would cause the magnet to fall faster through the tube. Here are some error sources and how to improve them. First of all, there might have been other magnetic objects around. These include objects like desks, pens, phones, and watches. While this was mitigated as much as possible, it was still imperfect, and we can mitigate this further by performing the experiment as far away from these objects as possible. Secondly, and probably the most affecting, was that the measurements were not perfect. Measurements were as good as they can be with human eye and tools, and led only to slight imperfections in calculations. However, the aluminum foil roll could have been thicker in reality than measured, which might have accounted for the differences in the model. In conclusion, today we became familiar with magnetic fields, flux, and the associated forces. We were able to form an accurate model of a magnet falling through the conductive tube. Like I said earlier, this was made possible with the magnetic flux equation, Faraday's law, PHYS2212 law, and Newton's third law. Using these, we were able to form accurate models for magnetic fields. Thank you.